A jet engine's turbine blades experience 5,000 degrees of heat and 50,000 g-forces simultaneously. Materials shouldn't survive this, yet they do for 20,000 plus hours. The reason isn't that we've discovered some magical metal. It's that we've engineered a system where failure is mathematically impossible by design. Most people think the blade itself is the engineering marvel, but that's backwards. The interesting part is that the blade would melt in seconds without the cooling system that surrounds it. Let's start with what's actually happening inside a jet engine. Air enters the front, gets compressed by the fan, then burned with fuel in the combustion chamber. That explosion reaches 2,000 degrees. The hot gas then rushes through the turbine section, where it spins blades at 50,000 revolutions per minute. Those blades are extracting energy from the hottest gas in the engine to power the compressor at the front. The reason this matters is that the turbine is the hottest, most violent part of the entire engine, and it's also the part that has to keep working reliably for decades. Now here's where the engineering gets interesting. A turbine blade is not solid. If you cut one open, you'd see it's completely hollow inside, like a tiny bone. Running through that hollow core are microscopic cooling channels, some thinner than a human hair. Cool air from the compressor stage gets diverted before it enters the combustion chamber. That cool air gets pumped through these internal channels at high pressure. The air exits through thousands of tiny holes on the blade surface, creating a protective film between the blade material and the 5,000 degree gas surrounding it. What matters is that this cooling system is doing the real work. The blade material is almost secondary. The interesting part is the material science underneath. These blades are made from single crystal superalloys. That means the entire blade is grown as one continuous crystal structure over the course of weeks in a specialized furnace. A normal metal has grain boundaries, places where different crystal structures meet. Those boundaries are weak points. Under 50,000 g-forces, a grain boundary becomes a crack initiation site. A single defect, one grain boundary, and centrifugal force will tear the blade apart in minutes. That's why each blade costs $500. Not because of the metal itself, nickel and cobalt aren't that expensive. Because of the weeks of precision growth, the testing, the inspection equipment that has to verify the crystal structure is perfect. But here's the thing that actually keeps the blade from exploding. The cooling system is doing something counterintuitive. The reason is not that we're preventing heat, it's that we're using heat strategically. These superalloys actually get stronger at higher temperatures, up to a point. The material properties improve as it gets hotter, so the cooling system isn't trying to keep the blade cold, it's trying to keep it at exactly the right temperature where the material is strongest. Too cold, and the metal becomes brittle. Too hot, and it loses strength. The cooling channels maintain a precise temperature gradient across the blade thickness. The outer surface stays hot enough to maintain strength, but cool enough that it doesn't melt. The reason this works is thermodynamic precision, not brute force cooling. Now let's talk about the forces involved. A turbine blade experiences centrifugal acceleration of about 50,000 times Earth's gravity. Imagine a blade that weighs 100 grams. The centrifugal force pulling on it is equivalent to 5,000 kilograms of weight trying to rip it off the rotor. The blade is attached at the root, which is the thickest part. The root has to be strong enough to hold the blade against that force while also being aerodynamically shaped so it doesn't create turbulence. The reason engineers can make this work is through material selection and stress distribution. The root is thicker, the blade tapers toward the tip, and the stress is distributed so no single point experiences the full force. Here's a question that might seem obvious, but actually isn't. Why don't we just make the blade thicker? The reason is not structural, it's aerodynamic. A thicker blade creates more drag, which means the turbine extracts less energy from the gas. A thinner blade is more efficient, but it's also weaker. So the blade thickness is optimized at the point where it's just barely strong enough to survive the forces, but thin enough to be aerodynamically efficient. This is why blade design is so critical. Engineers use computational fluid dynamics to model the exact flow of gas around the blade, then use finite element analysis to model the stress distribution. Then they iterate until they find the shape that balances strength and efficiency. The interesting part is how we know the blade will last 20,000 hours. The reason is not that we test one blade for 20,000 hours. That would take years. Instead, we use accelerated testing. We spin blades at higher speeds than they'll ever see in an engine, at higher temperatures with more thermal on cycling. We deliberately introduce defects and see how long they take to grow into cracks. We use statistical analysis to predict failure rates. Then we design the blade so that the predicted failure rate is essentially zero over the service life. The 20,000-hour lifespan isn't a limit. It's a statistical guarantee based on millions of hours of accumulated test data. But there's another layer to this that most people don't think about. The blade doesn't work alone. It's part of a system. The rotor that holds the blades has to be strong enough to hold them. The bearings have to support the rotor. The casing has to contain the hot gas. The seals have to prevent gas from leaking past the blades. The reason the entire system works is that every component is designed with the same philosophy. Build it strong enough to survive the worst-case scenario, but not so strong that it's inefficient. Every component is a constraint on every other component. The reason we can push turbine blades to these extreme conditions is that we've essentially eliminated the variables that cause failure. We control the material composition to within a few parts per million. We control the crystal structure through careful furnace procedures. We control the cooling flow rate to within a fraction of a percent. We control the operating temperature and speed through engine control systems. We control the thermal cycling by limiting how fast the engine can accelerate. We've taken a system that should fail constantly and made it fail almost never by removing every source of uncertainty. What matters is that this isn't magic or luck. It's engineering. It's the result of decades of research, billions of dollars in testing, and a deep understanding of material science, fluid dynamics, and structural mechanics. Every turbine blade and every jet engine flying today is the product of that accumulated knowledge. The reason a blade can survive 5,000 degrees and 50,000 G-forces is that we've engineered every aspect of the system to work together. The blade material, the cooling system, the rotor design, the engine control system, they're all optimized as a single integrated system. That's why it works.